Hello everyone, I'm happy to introduce our speaker, Dr. Yaron Beeri-Shlevin from a kinetic limnological laboratory. Yaron completed his PhD at Ben Gurion University of Negev, working on granites and geochronology. He did 2 postdocs, the first in North Sim, in Swedish Museum of Natural History, working on Arabian-Nubian shield evolution, and the second in Hebrew University, working on the sediment provenance. And since 2014, he's working in kinetic limnological laboratory, focusing on limnology, in organic geochemistry, in water and sediments. Please.
Thank you. I'm not sure this is a great translation of the Hebrew title, but I just wrote it this morning. So I'm going to talk about a project from my postdoc in Jerusalem, and it's on the source of Israeli sands. The source is the Provenance. Israeli sands, I mean the coastal sands, and continental scale erosion would mean African erosion in Africa. אני עובר? אתה מעביר?
אין זה?
אוקיי, and I'm going to talk about the Nile a bit, because the Nile is the source of the Israeli sands. But you'll see that we're going into some details. We will go into details about sources within the Nile or around the Nile. And the Nile is the longest river on Earth. It's about 7,000 kilometers and traversing various climatic areas and going into the Mediterranean. And it has 2 main tributaries, the White Nile and the Blue Nile, and within the Blue Nile I put in the Tekeze Akbar River, so we call that Blue Nile. And these 2 areas drain different areas, and also there's a great difference between water supply and sediment supply. So the White Nile supplies a lot of water, but it supplies very little today. It supplies very little sediments, and that's because of the silt swamps over here, this area, where the sediments just sink down and water goes. Whereas the Blue Nile, it drains the Ethiopian plateau, and it supplies not only water but much of the sediments into the main Nile and then into the Mediterranean. And when we go to the Mediterranean, to the delta of the Nile, the sands are swept into the eastern Mediterranean along the coast of Israel, and there are works showing that signals of the Nile delta can be found south of Cyprus. Thanks. Okay. So the Nile's sedimentary budgets and the erosion in its sources and sediment transport patterns have been the focus and are still a focus. I'm reading still papers today. Still a lot of work being done on the sediments of the Nile. But still, in this work, we focused on the provenance of the Nile's siliciclastics. What I mean here is when you go to the Israeli coasts, and the quartz sands that we're touching when we sit by the beach, by the sea, we're asking where does this come from? And I'll come to this point later. And we're using, in this work, we're using the isotopic signal, various isotopic signals of different detrital minerals. One of them is zircon, which I've been using a lot in previous works. And zircon is a good mineral because to do this, because you can date uranium lead age within the zircon, and that tells about the source rock, the age of formation. let's say, for a granite that included the zircon. And it also has lutetium hafnium systematics, which I will not tell you much about it. But it tells us something to differentiate between new formation, directly inputs from the mantle into the crust, rather than, or versus recycling of crust. And we'll see that these signals later. Monazite and rutile, which I've also been using in this work. There is now some attempts to apply lutetium hafnium systematics, but when I did this work, this was, let's say, not applicable. Still, these minerals, you can date them, and the ages are different generally between zircon and monazite rutile. In general terms, zircon would date the age of the formation of the rock. We're talking about granites or magmatic rocks. And monazite rutiles, in general terms, would the age or the date would focus around metamorphism. Okay, so when we go to the Nile's source terrains and we want to do this type of work, focusing on the focusing on the provenance using isotopic signal, we would like to see the signals, age signals, age distributions, and lutetium hafnium signals within the source areas. So the Nile tributaries take us into two different areas. The White Nile is eroding an area which is very old into the Archean. 3.4 is the oldest things around there. It's the Congo Creton around here, and then a little bit younger mantle around this Creton. But also there's areas which are an old stuff which has been recycled much later, during, let's say, 600. The Blue Nile, on the other hand, erodes basement areas which are a little bit different, or much different. When we talk about the basement, this is pink here, and versus the brownish areas here, which are also 600-year-old basement. The difference is that the Arabian-Nubian shield in pink is versus these ages, but mostly around 600. But the main difference between the 600, which is in the pink area, and the 600-ish in the brown area, is new stuff versus old stuff which has been recycled. So then we can differentiate, even if we get the same age, if we can see recycling versus non-recycling or new, we can differentiate between the brown and the pink. There's also in the source area, we have sediments which are Mesozoic directly within the drainage area of the Blue Nile today and the main Nile. We have Mesozoic sediments. Some of them are carbonates, some of them are sandstones. But around here we have also Paleozoic sandstones. Not within the drainage area of the Blue Nile. And we have very young volcanic rocks. If you go to the Israeli coasts and you pick up sand, quartz sand, in many cases you will see black stuff. This is the erosion of basalts from this area. So in no terms, I'm not saying that volcanic stuff from all around here is not eroding into the Nile. This has been shown, has been spoken about, but these rocks cannot contribute quartz, nor zircon. Okay. About our sampling areas and samples, we sampled just recent beach sands at Nitzanim. and some shallow coastal sands, 20 and 30 meter depths. Samples I got from the Geological Survey, Israeli Geological Survey. And then I went to Tel Sheruchan, which we can find, where we can find much older, or the oldest coastal sands of Israel. This is one of them is a dated, not by me, but somebody else, a dated rock, so we know it's about 2 million year old coast, sand. And then there's something younger, about 500,000 years. Next. We take the samples, just about the treatment. What do you do with the sand samples? We do mineral separation, and there should be special care because we're dealing with provenance. We do not want to pick specific minerals. We want to put and analyze just something which represents the population. But on the other hand, we're doing mineral separation. We're extracting zircon and rutile and monozites, which are very rare within the sand, so we need to do גם בעברית. So we're doing the mineral separation, but we keep the avoiding bias of the detrital populations. Then we mount these zircons, rutiles, and monozites on a epoxy mount, and we polish them to reveal the interiors. Then there's some imaging. Before we do analysis, we want to see the internal structure of the grains, because these analysis we can focus or target specific areas within the grain. So we can do it with cathodoluminescence or backscattered electrons. Yes?
Just a quick question. How are you doing your separation? What method do you use for your...
Mainly heavy liquids. Rotate, Wilfy table. It's another method. But then after you do that stages, after that stages, you have a lot of heavy minerals, and then to put, let's say, 100 or 200 for every sample, that would be, and not bias your, not pick specific minerals. That's not easy. Okay, so imaging for rutile, backscatter electron is good enough. Usually there's not much internal structure, but we would like to see them, to identify them within the population. Next. Zircons, on the other hand, if we use cathodoluminescence, we can see internal structure generally, most zircons. And this could tell us about, this is considered to be magmatic zonation, this is magmatic zonation. This could be metamorphic overprint, and we would like to avoid that. Next. And what we do is, as I said, 100 to 130 zircons were analyzed for uranium lead ages for every sample I took. And this is the yellow spots. Next. And of these we take about 100 and we analyze them for hafnium. These are the blue spots. They should be on top of the, or on the yellow spots, or within the same areas. So that's why we do imaging, to target specific areas in both analyses. And here I'm showing the specific way these machines or analysis work. We are using laser ablation ICP-MS. Laser ablation, we're ablating specific areas within the sample. For lutetium, hafnium, systematics, or isotopes, we need a bit more volume from the mineral. But still, if we identify the specific area, we can stay within the same domain, same growth domain within the mineral. Yes. So I talked about 100 to 130 zircons, and then we take about 30 rutiles from each sample for uranium lead ages, similar to zircon. Next. And I must admit I didn't do enough imaging to reveal all the monozites I had in my samples, so when I got to analysis, I had about 10 to do, from 2 samples, so that's what I did. Usually we would like to do much more, but it's good enough. The data set is big enough with the zircons and the rutiles. Next. And now I'll show a bit of results. The first thing I'm showing here, ages, uranium lead results, age results for zircons. These are ages 0 to 4,000 million years ages. And the samples are divided, the recent sands in yellow, recent beach sands, and shallow coastal sands here, and the old sands in red or purple. And most evident thing I'm showing here is that they are the same within the groups. Next. And they are the same within the groups and between the groups. Now I'm showing another sample from another work. Izuka et al. Worked and sampled in the Nile over here near Cairo, and they did similar work. And these diagrams are showing age, but not only distribution of age. The y-axis here is epsilon hafnium. I will not talk much about hafnium, only to say that things that are new should be around this gray, or just below this gray line, which we call depleted mantle. Things which are far below are recycled stuff. So something can be 600 million year old, but it can be very old in terms of its origin. It has been recycled, and generally we take lines like this. So we go back to something which is 2,000 million year old in origin, has been recycled during a 600 million year old event. It would end up here. Something which is a new addition to the crust, same age, would be here. That's the main difference on the y-axis. When I'm coming back to the samples, everything looks the same, and also looks the same as within the Nile. Now, as I said in the beginning, the Nile takes out sands. The sands are going this way or along the Israeli coast. So I'm sampling Nile sediments. This should look like Nile sediments. I'm showing this because when we first, our first manuscript, when it got to review, the first question was, yeah, people say the Israeli coastal sands come from the Nile, but, and then when this paper came out and these results came out, we can show that, at least from perspectives of zircon, it also looks the same. Okay, so all samples look the same, and there's variation in terms of age and in terms of new versus recycled. And the main group is over here. There is still something older, but the main group is over here, and within it the main group is younger, around 600. And when we look for the source of these things, we compare them to various things in basement of the source in the White Nile, in the Blue Nile. I'll talk about this later. But first thing we did was compare it to things we already knew from Israel, from works done in Israel. And this is a work by Moag et al. 2011 on Paleozoic sandstones in Israel and Jordan. And what we can see is that our samples, the Nile-derived sands, have the same. Not only are look the same between various groups and samples, but also are similar to the signature of the very old Paleozoic sandstones of Israel. So our first interpretation is that rather than erosion of basement in the source, Arabian-Nubian shield basement or other basement, this is actually the Nile sediments or the siliciclastics, the quartz sands, are erosion of older sandstones. That's it, most of it. Next. And when we go back to the areas within the Blue Nile, which are contributing most of the sediments today, we can see that although many people have put emphasis here, I've put a color which is, this is the pink from the other maps, the basement, the Arabian Shield basement. Although the River Nile crosses and erodes bits of this basement, there is a gorge over there. It also erodes a lot of sediments, Mesozoic sediments, and if you think about the Mesozoic sediments and even much younger sediments all around the area, they are actually considered to be recycled Paleozoic sediments. So it's no wonder that when you erode, even here in the source area of the Blue Nile, you erode something which is derived from Paleozoic sediments, you get a signature of Paleozoic sediments. Okay, next. Okay, but still, we would like to ask, what about erosion of basement areas? So, next. We look at this pattern. This is the pattern you've already seen, and this is actually, when we look at something here, we say the age is about 1,000, or it can be 600. It comes back from these ages. It's recycled, older stuff. Next. And we divide within this diagram, we divide areas. So this area, the red, next, and the blue are very different in terms of, not in terms of age, but in terms of being recycled stuff or new stuff. What happens in between is, next, is actually mixing. These are mixing trends. Between very young, very old, you get mixing of magmas contributing young stuff, old recycled stuff within the same age. That's what you get. So this is the interpretation of these lines. And what we see here is that we have a component of new stuff, but we have a lot of things which are either very old or mixed with very old, all with, let's say, dominantly 600, and there's a component of 1,000, 1,100 around here, but a lot of 600. And this fits, to some extent, this area. Recycled, old stuff, recycled during 600. When I say 600, it can be 650, so and so. Next. So we can say there is correlation with this recycled 600, we call it Pan-African event, or strike. Next. But then we come to the but. Next. Too little old stuff, what we call craton, which means we are draining areas from here. This is the Congo craton, and there's Paleozoic recycling of this craton, but still, we're talking about 3 to 2 billion year old stuff. We see too little of this. Next, in our sediments. There's an area here which is dominantly 1.3 to 1.4 billion year old stuff. I don't even know much to say about this crustal evolution stage in Africa, but we see that it's within the White Nile drainage area. We don't see none of it in our sediments, land sediments in Israel or in Cairo. Next. And more important, we do see in our sediments, we see this component, something about 1,000, and it's an enigma. And when we compare it to crustal areas or basement areas within the drainage area of the White Nile, even the Blue Nile, we don't know any such basement around this area. So we see it in our sediments, we don't see it in the source areas. Problem. Next. So just a short summary, we took 7 samples, different types of recent sands, siliciclastic sands, And we see that they seem to be the same, to give the same signature in terms of uranium, lead, and lutetium hafnium together. We don't see any processes of sorting, or we cannot identify processes of sorting. So, next. And what we see is generally, or dominantly, we see this group. It's varying between 0.54 billion to 1 billion year old stuff, but I'll call it 600. 600 and a bit of 100, a bit of 1,000 million year old. There's lesser of this stuff, and there's minor but still existent older stuff. Next. And there's a wide range of lutetium hafnium values. This we use an epsilon hafnium value. As I said, up is very young, very young and new. Old or negative or down would be the same age, the same evolution age would be the same, but it has an older history. It's recycled. Next. And although we see the Arabian-Nubian shield stuff in the Blue Nile, it's not the main source. The main source is erosion of older siliciclastic sediments. These are the Paleozoic, later recycled into Mesozoic stuff, Mesozoic sandstones. And I put here a question mark. There is some correlation to Nile, to some parts of the Nile basement, but also many problems. And now I turn to the detrital rutiles and some monozites to see what we get from there. And I'm showing here the detrital rutiles versus all detrital rutiles from all samples, all detrital zircons. And the main difference is that we get this 600 peak here and almost nothing of the older stuff which we have seen in the zircons. Next. Next. See that? And this is another way to show the distribution. We see bits of things which are younger. I'm not going to discuss the younger stuff. But generally the lack of almost from here older doesn't exist in the rutile population. Next. And when we go to the monazite, next. We see almost only 600. I think 9 out of 10 gave something between 600 and 620, and another one gave 740. Nothing older than this peak. Then odd. Okay, so some implications when you compare zircons, which are used by many provenance studies, to other minerals. Zircons are very good, very robust, and very easy to date them using uranium lead, and use a lot of isotopic signatures such as oxygen, delta 18, and lutetium hafnium, and many other things. Still, we should remember, and this is kind of a point I'm showing to the Provenance guys dealing with zircons. It's we can say it's too robust. Too robust meaning it's that you get over-representation of older things that are not being destroyed within the evolution of the basement, and therefore also within the evolution or the pattern you've seen in sediments. Next. We come back to the question of does the White Nile contribute sediments to the main Nile and therefore to the sediments of the Mediterranean, Israel? Next. 600 would be still a good correlation with this stripe, because if you have something which is being not formed during 600, it's being recycled during 600, metamorphic ages of 600 would dominate. That's good. Rutile then correlates to this stripe. But, okay, still way too little cratonic stuff. These areas have never experienced a 600-year-old event, not recycling and not metamorphism. So we should get some of these ages. There is cratonic stuff which is 3 to 3.4 billion-year-old stuff recycled and metamorphosed during 2.2 billion or 1.8 to 2 billion-year-old stages. We don't see that in the rutiles. Where are these rutiles? Okay, next. And again, no KAB in our rutile stuff, so that's again a problem. Next. And to interpretations. The first thing is that if we go to our interpretation coming from zircons, that eventually what we see in the Nile sands and in the Mediterranean sands that we pick here and the Israeli coasts, this is actually erosion of Paleozoic sediments, Paleozoic sandstones. Then it's no wonder that we don't see much of the basement from various areas, either the Blue Nile or the White Nile. So it's being masked by the contribution of Paleozoic sandstones. Next. But still, I would like to say a few more things about the White Nile. There's much debate about the evolution of the Nile, the connection of various segments of the Nile. So maybe we can say taking option A and taking what's being said there, maybe we can still say something about the evolution of the Nile. There are various options to strengthen the pattern that we see only Paleozoic sediments and not erosion of basement from the Nile. So either there's minor erosion of southern cratonic basement, which means the things over here. The old craton, for some reason, is not being eroded for a long, long time. That's one thing. But then another thing we can say is that since we get much correlation with this stripe, and much of my emphasis about the problems was about the southern segments, maybe there's a difference in time, early connection of northern segments, and later connection, much later connection of these segments. And there are works, independent works, geomorphology works showing that in early stages of the evolution of the Nile, these areas were eroded, but the direction of the rivers was towards the west and even southwest. And the most important thing is talking about today, the soot swamps, which block sediments today, bringing to a situation where the White Nile contributes only 5% of the sediments of the main Nile today. And then the question is, how long did the soot swamps exist? And I've been reading some papers and some works showing that there have been lakes here, not only in this stripe, but also going up to here, possibly existing for 400,000 years. So this is another thing. If you block the sediments from the south and you erode sediments over here, the Paleozoic sediments, then what you get is only the signature of the Paleozoic sediments. Next. Okay, so a summary of this work. So the Israeli coastal sands are good representatives of Nile sands. Next. And the Nile sands and their representatives in the Sinai Israeli coast are erosion of Paleozoic sandstones. Next. And there's no real indication for contribution from White Nile basement, mostly southern segments, Cretonic, the older stuff. No signs for that, no good signs. But we cannot rule early connection of northern segments, those that are characterized by a 600 million-year-old evolution stage. Next. And the important message for people dealing with provenance is that this is known that you should combine many lines of evidence when you do geology or science. But in provenance, too many provenance studies, people use zircon and tend to forget. So it's good to combine different isotopic signals or signatures and various minerals, give you a more coherent picture. Next. Questions?
So that 1 gigaounce age group, do you see a similar one in reworked Paleozoic sandstones like the early Cretaceous ones, or in whatever information we got on equivalent to early Jurassic, early Triassic sandstones from
I don't know about
Northwest Africa or from Southern Asia?
Yeah, I don't know about any information from Jurassic or Triassic sandstones.
Okay.
Although Dorit
I don't know.
wants to do something.
Don't have a student working on that at some point.
Yeah, I'm not aware of information from Jurassic, but Cretaceous there is. I know about some, call it preliminary work. It has not been published to my knowledge. It shows again that it's the same signature as the Paleozoic, but a little bit more juvenile. More of, when you combine also with Tichim Hafnim, you will see a little bit more in the Cretaceous sandstones, a little bit more contribution of juvenile, the new contributions of 600.
So there is another source that has been drained to this area, and we don't know what it is.
Yeah. So what I'm saying is that Paleozoic sediments. Maybe I should say a word about Paleozoic sediments. These are sediments which cover northern Africa from Morocco to Egypt, also into Arabia. Very wide belt of sediments, and it represents a huge erosion event of Provenance about 500 million years ago. Later sediments, we interpret them, or many people interpret them, as recycling of these Paleozoic sediments. And what I'm saying in this work today, even the Nile sediments, which are very young, are actually representing those old sediments and that huge erosion event. Almost nothing else. The shift between Paleozoic and Cretaceous represents actually erosion of Paleozoic sediments, a bit of exposed juvenile basement, and that goes into the Cretaceous sandstones. But that's all old history compared to tonight.
But ask questions. Okay.
Did you have the chance, or maybe now have the chance to look at the Tamar sands?
That?
Tamar.
I did, and I cannot.
You cannot talk.
Okay, thank you very much, Yaron.
Even if we torture you.
I didn't say that. You torture me.